Bimolecular nucleophilic SN2 reactions. Here we can let us consider the following reaction between the bromoethane and hydroxide ions. Hydroxide ions. The reaction between bromoethane and hydroxide ion, that is methane, it is reacting with hydroxide, that is sodium chloride containing hydroxide ion. It is producing the methyl alcohol sodium. Here what is happening, we can observe that there is an SN2 reaction. The reaction rate is influenced both by the concentration of methyl bromide and aqueous potassium hydroxide. Okay, the rate is influenced both by the concentration of methyl bromide, it is the substrate alkyl halide, and potassium bromide. Okay, so in other words, we can tell the reaction shows that is second order kinetics. It is second order kinetics. What it is, that the reaction is that is the it takes place consider it takes place in a single step and involves the simultaneous cleavage of carbon X bond. Carbon X bond means carbon halides, formation of carbon oxide, that is alkyl halide formation of alcohol bond. It is involves in the single step. Simultaneously cleavage takes place. Okay, bond formation and bond breaking at a time it will takes place. So the what it is, that the molecule of alkyl halide, that is must collide with the hydroxide ion. Alkyl halide must collide with the hydroxide ion. So the attack of OH group, you see the C equation, the figure C equation. The attack of hydroxide ion on alkyl halide can takes place from either side, that is frontal or rear. Okay, side, both side it will takes place frontal, but experimentally that has proven the attack of hydroxide ion takes place from the near, that backside attack. Okay, experimentally it is proved that is a backside attack. You see the equation, students. So that bromoethane, that is hydroxide, and it attacks the backside attack, or so it is a slow reaction, formation of transition state. It is producing the methanol. So here the conversion of reactants to products involves an intermediate state, that is highly potential energy relative to the reactants and product. Okay, the intermediate only the highly potential energy to the reactants and products. So that is that state, it is called as transition state. Okay, so in the formation of transition state, the partial bond formation takes place between the carbon and OH hydroxide, and the partial bond cleavage takes place carbon and bromine. Okay, students. So transition state ultimately decomposes to give alcohol as the final product along with the bromide ion. Okay, alcohol is the formation. Alcohol is the final product and along with the bromide ion. Transition state of SN2 reaction. What it is happening? This transition state of SN2 reaction. You see this is the transition state for a SN2 reaction diagram. That is in the transition state, the central carbon atom become sp2 hybridized, and the three hydrogen atoms attached to it lie in a plane with the mutual bond angles, that is 120-degree angle. So the OH group and the bromine atom are partially bonded. The OH group and bromine are, you see the diagram. Okay, OH and bromine are partially bonded to each lobe of the p orbital. Each lobe of the p orbital, which is perpendicular to the plane of the three hydrogen atoms, which is perpendicular to plane of the three hydrogen atoms. So the next, the carbon oxygen, the carbon OH bond is partly formed, and a carbon bromine bond is partly broken. Okay, so the hydroxide ion has diminished negative charge since it has the started sharing its electrons with the carbon atom. So, and at the same time, bromine develops a partial negative charge, and since it has started removing its bonding electrons, students. Okay, what it is happening? The exactly transition state. So here, what it is next? The potential energy for a diagram for SN2 reaction. Okay, the transition state. What it is happening in the changes to the products, that is methyl alcohol and bromide ion. Uh, the reaction proceeds with the complete inversion of configuration. Okay, so we can represent the changes from reactions to products in terms of this energy profile diagram. That in this here in this diagram here, the potential energy is plotted against the progress of the reaction. Potential energy, it is it is y-axis, the progress of the reaction, it is the x-axis. We can plotted the diagram. Okay, graph it, here we can see that it can be seen that transition state is a high energy state between the reactants as the and the products. High energy state, reactant and products. So we can't isolate a transition state. It is simply represents a transition between the reactants and products. So lifetime of a transition state is very small. Okay, it is the difference in the energy between the reactants and the transition state is known as energy activation. The energy, the life's time, it is transition is very small only, but the difference in energy between the reactants and the transition state is known as, it is like unstable, that is okay, known as energy of activation. So the transmission state finally decompress the of products, decompress the of two products. So this is the transition potential energy diagram of the SN2 reaction. Next, stereochemistry of a SN2 reaction. Here, what it is happening? Stereochemistry in SN2 reaction. Uh, we have discussed previously that above that SN2 reaction, the nucleophile attacks from the backside of the leaving group. So thus the configuration of the molecule produced after the reaction is inverted. After the reaction is inverted. Okay, the inversion of configuration is called as Walden inversion. So the inversion of configuration in SN2 reaction, we can be explained by the performing a reaction with the pure enantiomer of a chiral alkyl halide. Okay, chiral means the carbon containing 4 side of the groups. Okay, we can explain with the pure enantiomer of a chiral alkyl halide. For example, when you see the equations, when the 2-bromo-octane is allowed to react to the SN2 conditions, that is with aqueous solution of sodium hydroxide. So the inversion of configuration is observed, plus 2, that is positive 2 octanol is produced as a major product in SN2 reaction. So the Walden inversion of SN2 reactions, it is also proved by isotopic labeling experiment. You see the B equation, that is okay, isotopic labeled experimental, isotopic labeling experiment. That is here, when 2 iodo octane, it is allowed to react the solution of potassium iodide containing labeled iodine. Okay, so iodine atoms, it is observed that the rate of iodine exchange was twice of the rate of loss of optical activity. Okay, so it is proves that SN2 reaction backside attacks occur. Otherwise, loss of optical activity cannot be justified.